let's continue. Okay, let me open the table of content first. Okay. Excuse me. Okay. We are in chapter 22 here, Beyond Physical Memory Policies. Okay, let me open that. Okay. Beyond Physical Memory Policies. Well, let me read from the beginning, I guess. In a virtual memory manager, life is easy when you have a lot of free memory, right? A page fault occurs, you find a free page on the free page list and assign it to the faulting page. Hey, operating system, congratulations, you did it again. Unfortunately, things get a little more interesting when little memory is free. In such a case, this memory pressure forces the operating system to start paging out pages to make room for actively used pages. Basically, the operating system start moving out the page from the memory to possibly this or maybe another device, I guess, to make room for actively used pages in the memory. Okay, deciding which page or pages to effect is encapsulated within the replacement policy of the operating system. Historically, it was one of the most important decisions the early virtual memory system made. Okay, deciding which page or pages to effect is encapsulated within the replacement policy of the operating system. Historically, it was one of the most important decisions the early virtual memory system made. The most important decision the early virtual memory system made, as older system had little physical memory, right? Minimally, it is an interesting set of policies worth knowing a little more about. And thus our problem, the crux of the problem here, how to decide which page to effect. How can the operating system decide which page or pages to effect from memory? This decision is made by the replacement policy of the system, which usually follows some general principles discussed below, but also includes certain tweaks to avoid corner case behavior. Okay, how can the operating system decide which page or pages to effect from memory? Right. Deciding which page to effect, right? This decision is made by the replacement policy of the system, which usually follows some general principle, which will be discussed below, right? But also includes certain tweaks to avoid corner case behavior. Okay, case management. Before diving into policies, we first describe the problem we are trying to solve in more detail. Given that main memory holds some subset of all the pages in the system, it can rightly be viewed as a cache for virtual memory pages in the system. Given that the main memory holds some subset of all the pages in the system, main memory holds some subset of all the pages in the system. Okay. It can readily be viewed as a cache for virtual memory pages in the system. Oh. Alright. Thus our goal in picking a replacement policy for this case is to minimize the number of cache miss. That is to minimize the number of times that we have to fetch a page from this. Alternately, one can view our goal as maximizing the number of cache hits. That is the number of times a page that is accessed is found in memory. Okay, so we want to minimize the cache hits, the cache miss here, not hit, the cache miss. That is the number of time we have to fetch a page from this, and maximize cache hit, the number of time a page access a page found in the memory, a page that need to be accessed found in memory, maybe something like that. Knowing the number of cache hits and miss, let us calculate the average memory access time in MAT. Average memory access time for a program a metric computer architects compute for hardware cache. A metric computer architect compute for hardware cache. Oh, I assume this is some kind of metric for the hardware cache, I guess. Maybe average memory access time. Specifically, given these values, we can compute the average memory access time of a program as follows. AMAT equal TM plus PMIS multiplied by TT. Okay, the TM in here represent the cost of accessing memory, right? I guess the time, maybe we can think of T here as the time needed to access the memory, and then TT is the time needed accessing this, like how much time needed to access the memory, maybe something like that. And then the P miss here, the probability of not finding the data in the cache, that is a miss. P miss varies from 0.0 to 1.0, and sometimes we refer to a present miss rate instead of a probability. For example, a 10% miss rate means P miss equal 0.10 or something like that. Note, you always pay the cost of accessing the data in memory, right? You always always pay the cost of accessing the data in memory when you miss. However, you must additionally pay the cost of fetching the data from this. Right? So whether we miss or hit, we always accessing the data in the memory, like checking whether the memory exists, whether whether the page, maybe let's call that, whether the page is in the memory or not. Or maybe the data, in this case, I guess, whether the data in the memory or not, and if it is in the memory, we can directly access the data. But if it is not, we need to fetching the data from this. Okay, keep in mind that we always accessing the data in memory, whether we hit or miss here. Okay, for example, let us imagine a machine with a tiny address space, 4 kilobyte with 256 byte page. Okay, thus a virtual address has two components: a 4-bit virtual page number, the most significant bit, and an 8-bit offset. The least significant bits, the binary digit here. Okay, the offset, right, is from this one, the page size. So every page is around, what is it called, 256 byte, maybe something like that. If we take a look at this, it is something like this, 2 power 8, right? This is the bit or the binary digit. So basically there is, I guess, 8 bits here, something like that. Okay, and then the rest is the virtual page number, the most significant bit. So again, we have this address space, 4K address space here, and then to get that bit, I guess we can use math. Something like this. We have 12 bit here. Again, we can do this to verify. 2 power 12, and then because we have what is it called? Because we have 8-bit offset, right? Again, the total bit in the, what is it called, in the address space is 12, and then we have 8-bit here, so the rest here, that is 4-bit, is the virtual page number. So maybe something like this. I'm not sure how much this is. Okay. Oh, maybe one here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So this one is the virtual page number, or maybe the index, something like that, and this one is the offset, and the total is 12, right? So there is that. Thus a process in this example can access 2 power 4 or 16 total virtual pages. Okay, right, 16 total virtual pages. Again, 4 is from this one, 4-bit virtual page number. So we have 16 pages in this address space, right? And one page have this, I guess, 256 byte. So maybe something like this, right? Okay. So each page have this 256 byte, and we have 16 pages in the 4K address space. Something like that. In this example, the process generates the following memory reference, that is virtual address. This one, oh, interesting. So we have, I guess, 10 in this case. The 10, what is it called? 10 virtual address. Let me copy this. I'm not sure if I can do this. Let me try. Okay, no, not that one. Okay, and then maybe this one. Okay, no. Is it this one? Oh, interesting. Yeah, not 0 but 1. Oh, okay, there is. Welcome to regex, I guess. Okay, let's try. Okay. And then try this one too. Right. So we have this 10 virtual address. This virtual address refers to the first byte of each of the first 10 pages of the address space. Okay, refer to the first byte of each of the first 10 pages. Okay. So this is the first byte. First byte, maybe something like this. And then this is the page 0. Yeah, wait, let me. And then maybe do something like this. So we have 256 byte, right? Previously here from this information, and this is just the first byte from this 256 byte. So we have, let's say, more byte here. This is just the first byte from the each page, from the the 10 bits, I guess, the first 10 bits, right? Okay, the first byte of each of the first 10 bits of the address space. But again, we still have 6 more, right? Because we have 16 bits here. Maybe I can do something like this. Bits 10 plus 11. Okay, maybe let's change this to this, I guess. And then page 13, yeah, until page 15, because we start from 0 here. So we have 16 pages, but we only have 10 page information here. And even those 10 pages only the first byte. Okay. So we have maybe around 255 bytes to go, I guess. Maybe something like that. Okay, let us further assume that every page except virtual page 3 is already in memory. So I assume, if I remember correctly, I guess, virtual page 3 start from 0, right? So this one will be missed. Other than that, it is hid. Okay, let's further assume that every page except virtual page 3 is already in memory. Thus, our sequence of memory reference will encounter the following behavior: hit, miss, right? Page 0, page 1, page 2, and then page 3, miss, this one, right? Miss, and then hit again until the 10 page, I guess. Let me check. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, right. So until this one, because that is the only information we have currently. We can compute the hit rate, the percent of reference found in memory, 90%. Okay, so we can compute the hit rate, the percent of reference found in the memory, and that is 90%, as 9 out of 10 reference are in memory. The miss rate is thus 10%. I mean, the miss rate is thus 10%. Again, 100 minus 90%. 100% minus 90%. And we get the 10% here. So P-miss is 0.1. In general, P-hit plus P-miss equal 1.0. Hit rate plus miss rate sum to 100%, right? To calculate the average memory access time, the AMAT here, average memory access time, we need to know the cost of accessing memory and the cost of accessing disk. Assuming the cost of accessing memory, the DM is around 100 nanoseconds, and the cost of accessing disk, the TD, is 10 milliseconds. Oh, okay. So I assume the time we need to access the memory is around 100 nanosecond, and the time we need to access the disk is 10 millisecond. The difference measurement, I guess. Okay, that is something to keep in mind. We have the following average memory access time: 100 nanosecond plus 0.1 multiplied by 10 millisecond. Okay, which is 100 nanosecond plus 1 millisecond, and then we need to transform the millisecond into nanosecond, I guess, or you can transform the nanosecond into the millisecond like this one, so it become 1.0001 millisecond, or about 1 millisecond. If our hit rate had instead been 99.9%, the p-miss is 0.001. Okay, the result is quite different. Average memory access time is 10.1 microsecond. Oh, not millisecond. Okay, or roughly 100 times faster. Yeah, notice the difference here: microsecond, millisecond, and nanosecond. Okay, as the hit rate approaches 100%, average memory access time approaches 100 nanosecond. Oh, as the hit rate approaches 100%, average memory access time approaches 100 nanosecond. Okay, this one. I mean, if we have 100% hit, right, without any miss, then I guess we only need 100 nanosecond for the average memory access time. Again, the p-miss should be 0 if we have 100% hit. Okay. Alright, and yeah, don't forget about the bracket, I guess, to prevent confusion, like this one. Okay. Unfortunately, as you can see in this example, the cost of this access is so high in modern system that even a tiny miss rate will quickly dominate the overall average memory access time of running program. Okay, even a tiny miss. Okay, clearly we need to avoid as many miss as possible or run slowly at the rate of the disk. One way to help with this is to carefully develop a smart policy, as we do now. Okay. The optimal replacement policy. To better understand how a particular replacement policy works, it would be nice to compare it to the best possible replacement policy. To better understand how a particular replacement policy works, It would be nice to compare it to the best possible replacement policy. To the best possible replacement policy. Oh. The best possible replacement policy. Okay. As it turns out, such an optimal policy was developed by Belletti many years ago. Okay. He originally called it MIN. Okay. The optimal replacement policy leads to the fewest number of misses overall. Belletti showed that a simple but unfortunately difficult to implement. Belletti showed that a simple but unfortunately difficult to implement approach that replaces the page that will be accessed further in the future is the optimal policy, resulting in the fewest possible case miss. Okay, I'm kind of curious what makes this difficult to implement. Yeah, maybe we will find that out. Hopefully, the intuition behind the optimal policy makes sense. Guess this one. Replace the page that will be accessed furthest in the future. What is the furthest in the future? Is it not the nearest future? Okay, maybe let's say rather than replacing the page that we will access the next second, we are replacing the page that will be accessed a year later. Maybe something like that. Maybe again the furthest in the future. Okay. And yeah, I guess the difficult part to implement here, checking the furthest part here. Like how did we know what kind of memory will be accessed furthest in the future? Like a year in the future, or maybe 2 years in the future. Maybe that is the difficult part. Okay. Hopefully the intuition behind this optimal policy makes sense. Think about it like this. If you have to throw out some page, why not throw out the one that is needed the furthest from now, right? Throw out the furthest from now. By doing so, you are essentially saying that all the other pages in the case are more important than the one furthest out. The reason this is true is simple. You will refer to the other page before you refer to the one furthest out. Okay. You will refer to the outer page before you refer to the one furthest out. Let's trace through a simple example to understand the decision the optimal policy makes. Let's trace through a simple example to understand the decision the optimal policy makes. Assume a program accesses the following stream of virtual pages. Okay. This one. Assume a program accesses the following stream of virtual pages. Okay. Figure 20.1 shows the behavior of optimal, assuming a case that fits 3 bits. In the figure, you can see the following action. Not surprisingly, the first 3 access are missed as the case begins in an empty state. Such a miss is sometimes referred to as a cold start miss, okay, right, or compulsory miss. Then we refer again to page 0 and 1, which both hit in the case. Finally, we reach another miss to page 3. Okay. We refer again to page 0 and 1, which both hit in the case. Finally, we reach another miss to page 3, but this time the case is full. Oh, okay. So we are only accessing 0 and 1. And we are not accessing the 2 here. Okay. Alright. 0 and 1, which both hit the case. Finally, we reach another miss to page 3, but this time the case is full. Again, the assumption here is that the case only fit 3 bits, so only fit 0, 1, and 2. Okay. A replacement must take place, right? Which begs the question, which page should we replace? With the optimal policy, we examine the future for each page, currently in the case 0, 1, and 2, right? And see that 0 is accessed almost immediately, 1 is accessed a little later, and 2 is accessed further in the future. Thus, the optimal policy has an easy choice: evict page 2, resulting in page 0, 1, and 3 in the case. Okay. The next 3 references are hits, but then we get to page 2, which we evict long ago and suffer another miss. Okay. Here the optimal policy again examines the future for each page in the case 0, 1, and 3, and sees that as long as it doesn't evict page 1, it is about to be accessed, we will be okay. The example shows page 3 getting evict, although 0 would have been a fine choice too. Finally, we hit on page 1 and the trace completes. Okay, this one, right? Well, let me read this first, I guess. We can also calculate the hit rate for the case with 6 hit and 5 miss. The hit rate is hits divided by hits plus miss. Okay. Hit is 6 divided by 6 plus 5. The total here, right? Or 54.5%. You can also compute the hit rate modulo compulsory miss, that is, ignore the first miss to a given page. Okay. Resulting in an 85.7% hit rate. Okay. Unfortunately, as we saw before in the development of scheduling policy, right, the future is not generally known. Again, this is the difficult part, I guess. you can build the optimal policy for a general purpose operating system. Thus, in developing a real deployable policy, we will focus on approach that find some other way to decide which patch to evict. The optimal policy will to serve only as a comparison point to know how close we are to perfect. Oh, okay. Let me take a look at this figure 22.1, tracing the optimal policy. Okay, we are trying to access this, right? And then we that make me wonder if we are trying to hit 0 and 1, why we also case 2, you know? I mean, are we automatically catch the 3 pages, you know? Are we automatically fulfill or filling up the gates even though we only access, let's say, a few pages? Okay, and then we are trying to access page 3 but miss, so we evict 2. We are getting 2 out of the case. 0 hit again, 3 hit again, 1 hit again, and then 2 in here miss, so we evict 3 so that can access 2 here. The case state, right? And then 1 hit again. Yeah, I'm kind of curious. Why the cold start miss? Why the cold start also accessing this, also having this page 2 in the case, I guess. I'm still not sure. Okay, so let me put this in figure 1. Why are we putting page 2 in the case? In the case 2, and we are not accessing page 2, and we are only accessing page 0 and 1. I mean, again, are we trying to access the 3 of this? If so, why this is only 0 and 1? I mean, I assume we retried the instruction, right? Oh. Okay. Okay. Right. Yeah, maybe because, okay, in this case we are trying to access, okay, 0, 1 and 2, and then we are accessing 0 and one. Okay, river again, right? I missed that. Okay, then it's fine. We have solved that mystery. So this is the first attempt, right? And this is the second attempt. Okay. Right. Okay. Tracing the optimal policy. And well, let me read the aside. Is there any aside? No. This one, tip, I guess. Let me read the tip. Comparing against optimal is useful. Although optimal is not very practical as a real policy, it is incredibly useful as a comparison point in simulation or other studies. Saying that your fancy new algorithm has a 90% hit rate isn't meaningful in isolation. Saying that optimal achieves an 82% hit rate and thus your new approach is quite close to optimal make the research more meaningful and give it context, right? Thus, in any study you perform, knowing what the optimal is lets you perform a better comparison, showing how much improvement is still possible, and also when you can stop making your policy better because it is close enough to the ideal. Okay, in any study you perform, knowing what the optimal is let you perform a better comparison, showing how much improvement is still possible, and also when you can stop making your policy better because it is close enough to the ideal. And well, maybe at some point we might also improve the optimal solution, I guess. Who knows, right? And then the aside here. Aside types of case miss. In the computer architecture world, architects sometimes find it useful to characterize miss by type into one of the three categories. Okay. Computer architecture world, architects sometimes find it useful to characterize miss by type into one of three categories: compulsory, capacity, and conflict miss. Okay, sometimes called the 3 C's. Okay, compulsory, capacity, and conflict miss. A compulsory miss, or cold start miss, occurs because the cache is empty to begin with, and this is the first reference to the item. In contrast, a capacity miss occurs because the cache ran out of space and had to evict an item to bring a new item into the cache. Okay. The third type of miss, a conflict miss, arises in hardware because of limit on where an item can be placed in a hardware cache due to something known as set associativity. Maybe that's how I pronounce it. I'm not sure. how to pronounce this. Z associativity. Okay. It does not arise in the operating system patch case because such cases are always fully associative. Okay, fully associative. Because of limit on where an item can be placed in a hardware case due to something known as set associativity, it does not arise in the operating system base case because such cases are always fully associative. That is, there are no restrictions on where in memory a page can be placed. C, H, and P for the tile. Okay. Oh. Is set associativity in here means that there is some restriction, maybe? The restriction where the page can be placed in the hardware. Maybe. Simple policy. First in, first out. Okay. Hello, Emily. Welcome. Hey, is that Sway you are using? Why is it so minimalist? How long have you been using Linux? It's not Sway, it is the i3 VM here. You can see the X11 window manager. I'll put that in the chat. Yeah, I'm not using Wayland yet, still on X11. Why is it so minimalist? Because it is simple, you know. I like simple things, I guess. It is purely objective. Purely subjective, I mean. It is purely subjective. So your mileage may vary. Just use whatever you are comfortable with. You don't need to be a minimalist, you know. But yeah, I'm comfortable with my i3 window manager setup. How long have you been using Linux? Maybe 5 or 6 years now, I guess. Okay. Alright, so... Oh, there's Pilates anomaly. Okay. Well, I guess let's continue this. A simple policy. First in, first out. Okay. Did I miss something? I don't think so. Well, yeah. Let's continue this section, a simple policy, FIFO or first in, first out, in the next session. That's it for now. Thank you for watching and see you next time. Bye bye.